So, first of all, I would like to thank the organizers for their kind invitation in this nice place and conference. My work has been done in collaboration with Alberto Capellaro and Flavio Toigo at the Department of Physics and Astronomy of the University of Padova. At the University of Padova, sorry. Okay, this is the summary. Okay. First, I will briefly review some properties of two-dimensional superfluids and the Berezinski-Kostelis-Thouless transition. Then I will discuss a recent experiment done at the École Normale Supérieure this year. And that is somehow surprising because the experimental results do not follow the prediction of Berezinski-Thouless transition. And I will explain these results, assuming that the system is in non-collisional regime, collisionless regime, by solving the two-dimensional Boltzmann-Landau-Vlasov equation. In particular, I will calculate the collisional sound, and I will compare with the experiment. And indeed, the agreement is quite good. So, just to briefly review what is quite known, very, very well known, if you have an ideal gas of non-interacting bosons in a uniform configuration, you know that there is a Bose-Einstein condensation only below a critical temperature if the system is three-dimensional. If the system is two-dimensional, if you want, the critical temperature is 0, and in dimension 1, there is no solution, no Bose-Einstein condensation. This is the result very old, and it's valid for non-interacting boson, and somehow it was extended for interacting bosons by the Mermin-Wagner theorem. And as you know, the theorem says that there is no Bose-Einstein condensation at finite temperature in a homogeneous system with sufficiently short-range interactions in dimensions smaller or equal to 2. Despite the absence of Bose-Einstein condensation, Kostelis et Thouless, but also Berezinski, suggested that a two-dimensional fluid can be superfluid, below a critical temperature. That is the so-called Berezinski-Kostelis-Thouless critical temperature. As you know, this Kostelis-Thouless transition has been observed experimentally in various physical systems, in the past for helium-4, also for superconductivity, more recently also in atomic gases, in rubidium atoms, and also in fermionic gases in the BCS-BC crossover, lithium atoms. An important prediction of Kostelis-Thouless transition is that the superfluid density, and also obviously the superfluid fraction, in 2D jumps to 0. So while in 3 dimensions it decreases by increasing the temperature, but it smoothly goes to 0, in 2D the prediction is that there is a jump at the critical temperature. That is the Berezinski-Kostelis-Thouless critical temperature. Moreover, according to the two-fluid hydrodynamics of Landau and Kalatnikov, the sound velocity of a superfluid has 2 branches. One is the first sound velocity, C1, and the second one is the second sound velocity, C2. The slower is the second sound. And also, in this case, for a 2D systems, one should expect that this second sound velocity has a jump to 0 at the Berezinski-Kostelis-Thouless critical temperature. In the recent experiment done at the École Normale Supérieure of Paris, they have studied a quasi two-dimensional bosonic system in a uniform configuration, and they have excited the density oscillations, and so the sound in this way, but they have seen that at small temperature, these are the experimental data. At small temperature, they are around 1 in units of the zero temperature second sound velocity. So you see, in this region, somehow the data follow the prediction of the to sound velocity of Landau-Kalatnikov, but then increasing the temperature, the experimental points go down, but they don't go to 0 at the critical temperature. And instead, you see, at the critical temperature, still you have 0.8. And moreover, if you want, if you further increase the temperature, the experimental data somehow are turning on. So they are in agreement with the two-fluid hydrodynamics only well below this region, well below the Berezinski-Kosterly-Thouless critical temperature. This strong discrepancy near and above the critical temperature has been explained, suggesting that the experimental conditions of that experiment are such that there is no local thermodynamic equilibrium, and so the system is in the collisionless regime. Moreover, the experimental data show the presence of a strong damping of this sound mode around and above the critical temperature. In the next slide, I will show how we can theoretically explain these findings. So, the starting point for a theoretical description could be, in this case, assuming that the system is non-collisional, the Boltzmann-Landau-Vlasov equation, namely a Boltzmann equation where you completely neglect the collisional term that is on the right side of equation 1, but somehow the interaction between particles is still present as a mean field term on the left side of the equation. It's a sort of Hartree-Fock mean field term. Here, G2D is the characteristic strength, and obviously is related to the 3D scattering length, AS, and to the characteristic length, AZ, of the harmonic confinement along the third direction. To solve analytically this equation, one can do the following. Okay, this F is the distribution that depends on the position, distribution of particles, that depends on the position of the particle, the linear momentum, and in general time. And we assume a uniform configuration, but which has some dependence on momenta, that is F0, plus a small perturbation. Now, if we insert these ansatz in the equation 1, and we neglect terms that are quadratic or higher in the fluctuation, we get an equation for the fluctuation, a linearized equation, a linearized Landau-Boltzmann-Vlasov equation, that is this one. Okay? Notice that obviously this equation depends also on the chosen stationary isotropic configuration F0 that appears here. Now, if we do the Fourier transform of the fluctuation, where there is the position R, we have the linear momentum K. Where there is the time T, we will have the frequency omega. And after some manipulation, from equation 5, we can get this equation, that is equation 6, where somehow we have an implicit formula that gives the omega, the frequency, in terms of the wave vector k. So an implicit formula for the dispersion relation. Now, in general, the frequency is complex, so we can separate the real and the imaginary part of it, we assume that the imaginary part is positive to avoid exponential growth of perturbation. And moreover, doing this simplifying assumption that k, the wave vector, is along x, but is not a big problem, one gets this simplified equation where here there is c, that is our speed of sound, that is simply the ratio between the frequency omega and the wave vector k. Obviously, because omega in general is complex, also c is complex. Moreover, you see here we have some singularity, but somehow the presence of a complex c remove part of the problems. And so this c has a real component, cr, and an imaginary one, ci. And assuming that the imaginary component is much smaller than the real one, one can deduce two coupled equations for cr and ci that are written here, equation 11 and 12. By the way, obviously, if ci is 0, so you are assuming that the solution, so is that the velocity is real, you have only one equation, quite simple, this one. But we will see that indeed it's important to include also the imaginary part of it. Hidden here, there is still F0, that is our equilibrium distribution. And we choose for it typical Bose-Einstein distribution with the mean field term here. But we work in the fully degenerate regime. So that, and in this way we can do analytics. Obviously, we have to impose the conservation of the total number of particles, normalization, and in this way we find a nice formula that relates the chemical potential mu tilde to the temperature and also to this Tb, where Tb is somehow the temperature of Bose degeneracy, and Tb depends on the density n. Okay. Now, doing so, the two coupled equations can be written in this way. These two nasty equations, but somehow algebraic, at least they are algebraic. And for instance, with Mathematica, you can easily solve them. And what you can do, you can compare with the experimental data. So you see, the blue dots are the experimental data. The solid line is our theory, solid black line is our theory, including the imaginary part. And instead, the red dashed is without the imaginary part. And so you see that the inclusion also of the imaginary component seems to somehow improve, if you neglect this experimental point, seems to be in quite good agreement. Moreover, one can also study the how the imaginary component changes with temperature, and one finds that at 0 temperature this is 0, and it increases and becomes indeed quite large around and above the critical temperature. In particular, in the inset, there is the ratio between the imaginary and the real part of the sound velocity, and it is okay at TC is still 15%, but then it increases. And this is somehow in agreement with the experimental findings that around and above the critical temperature, the damping, that we can interpret as Landau damping, is important. So this is what I wanted to say. So here are the conclusions. We have analyzed the sound propagation in collisionless bosonic gases, assuming a 2D configuration, by solving the linearized Boltzmann-Landau-Vlasov equation, we have derived the two-coupled algebraic equation for the real imaginary part of the sound velocity. We have compared our theoretical results with the recent experiments of École Normale, finding a quite good agreement between our theory and the experiment. And our theoretical analysis somehow suggests that the density perturbation using the experiment has excited what I would call a bosonic zero sound, because zero sound is a typical word for collisionless sound for fermions. Here we have some the analogous for bosons, so I will call it bosonic zero sound, namely the sound for collisionless bosonic fluid. The last remark, the two-fluid hydrodynamics of Landau-Kalatnikov describes correctly only the collisional regime. Maybe in the future one can try to improve the Landau-Kalatnikov equations such that one can take into account also the collisionless one. Thank you very much for your attention.
Thank you very much. Are there questions?
So I very much enjoyed the talk. I'm wondering, is there